Hello! Today we're going to solve a fascinating equation involving exponents and roots. Our goal is to find all real numbers x that satisfy the equation. The equation we're working with is x to the power of the square root of x equals the square root of x, all raised to the power of x. Let's write that down. By the end of this video, you will be able to solve this specific exponential equation and understand the key algebraic and logarithmic properties needed to tackle similar problems. Before we begin manipulating the equation, we must establish its domain. This is a crucial first step for any problem involving square roots and fractional exponents. Notice the terms square root of x and x to the power of the square root of x. For the expression square root of x to be defined in the real numbers, x must be greater than or equal to 0. You can't take the square root of a negative number. Next, consider x to the power of the square root of x. If x were equal to 0, this expression would be 0 to the power of 0. In mathematics, 0 to the power of 0 is an indeterminate form, and often it's defined to be 1. However, to avoid this ambiguity and simplify our solution, we'll assume x is strictly positive for now. So, we will proceed under the assumption that x is a positive real number. This is our domain for finding solutions. Now that we've set our domain, let's look for a simple solution. What happens if x equals 1? Let's test x equals 1. Substituting it into the left side, we get 1 to the power of the square root of 1, which is 1 to the power of 1. That's simply 1. For the right side, we have the square root of 1 raised to the power of 1, which is also 1. Since both sides equal 1, x equals 1 is a valid solution. It's always a good idea to check for these obvious solutions first. We've found one, x equals 1. Now, let's see if there are any others. Our next step is to simplify the equation using properties of exponents. Let's start with the right side. We have the square root of x raised to the power of x. Recall that the square root of x can be written as x to the power of 1/2. So, we can rewrite the right side as x to the power of 1/2, all raised to the power of x. This is a power raised to another power. What do we do when we have a power raised to another power? We multiply the exponents. This is the property a to the m, all raised to the n, equals a to the m times n. Applying this, x to the 1/2 raised to the x becomes x to the power of x divided by 2. This gives us a much simpler form of the equation to work with. We've used a fundamental exponent property to simplify the expression. Now, let's address the term square root of x in the exponent on the left side. We can also write it as a fractional exponent. Just as before, the square root of x is x to the power of 1/2. Substituting this back into our simplified equation, we get x raised to the power of x to the 1/2 equals x to the power of x over 2. We now have an equation where the base on both sides is the same, x. This is very helpful. A key property states that if a to the m equals a to the n, and a is not 0, 1, or -1, then the exponents must be equal. In our case, if x is our base, which is not 0 or 1, we can conclude that the exponents are equal. So, we can set the exponents equal to each other. X to the 1/2 equals x over 2. This is a much simpler equation to solve. Let's pause for a moment. We've transformed a complex equation into a much more manageable one. But before we solve it, let's consider a special case for the property we just used. The property if a to the m equals a to the n, then m equals n works well when the base a is not 0 or 1. If the base a is 0, the expression is indeterminate. If the base a is 1, then the equation 1 to the m equals 1 to the n is always true, no matter what m and n are. So, we need to check if our solution x equals 1 is valid, not just because the exponents are equal, but also because it is a special case for the base. We already confirmed that x equals 1 is a solution by direct substitution. When x equals 1, we get 1 equals 1, which is true. This confirms our earlier finding. This step of checking special base cases is crucial to ensure we don't miss any solutions that fall outside the general rule. So far, x equals 1 is our only solution. Now, let's return to the simplified equation we derived and solve it for x. The equation is x to the 1/2 equals x over 2. We want to isolate x. Let's start by getting rid of the fraction on the right side. We can do this by multiplying both sides of the equation by 2. This gives us 2 times x to the 1/2 equals x. Remember, x to the 1/2 is the same as the square root of x. To solve an equation with a square root, a common technique is to square both sides. Let's square both sides of our equation. On the left side, we apply the power to both the 2 and the x to the 1/2. This gives us 2 squared times x to the 1/2 squared, which simplifies to 4 times x to the power of 1. So the left side becomes 4x. The right side is x squared. Now we have a simple quadratic equation. Let's rearrange it to solve for x. We've reached the quadratic equation, 4x equals x squared. Let's find its solutions. To solve this quadratic, we can move all the terms to one side, setting the equation equal to 0. Subtracting 4x from both sides gives us x squared minus 4x equals 0. Now we can factor out the common term, which is x. This leaves us with x times the quantity x minus 4 equals 0. Using the zero product property, we know that for this product to be 0, one or both of the factors must be 0. This gives us two potential solutions, x equals 0 or x minus 4 equals 0, which means x equals 4. So, our algebraic process has given us two potential solutions, x equals 0 and x equals 4. But we're not done yet. We must always check our solutions in the original equation, especially when we've squared both sides. Squaring can sometimes introduce extraneous or false solutions. It's time to check our potential solutions. First, let's revisit x equals 0. Remember at the start of the video, we decided to assume x was strictly positive to avoid the indeterminate form 0 to the power of 0. If we substitute x equals 0 back into the original equation, we get 0 to the power of 0 on the left side and 0 on the right side. As mentioned, 0 to the 0 is usually considered indeterminate. So, following our initial assumption that x is greater than 0, we must discard x equals 0 as a solution. It lies outside the domain we defined for a clear algebraic solution. Now, let's check our other potential solution, x equals 4. Substituting x equals 4 into the original equation, we get 4 to the power of the square root of 4 on the left, and the square root of 4 raised to the power of 4 on the right. This simplifies to 4 squared on the left, and 2 to the 4th power on the right. Both 4 squared and 2 to the 4th power are equal to 16, so x equals 4 is a true solution. And finally, let's check our special base case, x equals 1 once more. We already saw that x equals 1 is a solution, giving us 1 equals 1. This solution was found independently of our main algebraic track, because it was a special case of the property for equal bases. After careful checking, we have identified two real solutions to our equation. The real solutions are x equals 1 and x equals 4. So, let's recap the steps we took to solve this interesting equation. First, and most importantly, we established the domain. We determined that for the expression to be well defined in the real numbers, we must have x greater than 0, which also led us to check the special case of x equals 1. Second, we simplified the equation using exponent rules, specifically the power rule and the property that a square root is equivalent to a power of 1/2. This transformed the intimidating-looking equation into a simpler form with the same base. Third, because the bases were the same, we set the exponents equal to each other. This gave us a new, simpler equation to solve. Fourth, we solved this new equation, which was a quadratic. We found two potential solutions from this step. Finally, we performed a crucial step, checking all our potential solutions in the original equation to identify and eliminate any extraneous solutions. We confirmed that x equals 1 and x equals 4 are the only real numbers that satisfy the equation. You now have the tools to approach and solve similar exponential and radical equations by carefully establishing the domain, using exponent properties, and always checking your answers. Thank you for watching.